And I'm really sorry I can't be there with you. I'm sure that will be more fun, at least for me, but probably for both sides. But let's see if we can make the best of it. Do you hear me well at the back? Wave if yes.
That's fine.
Okay. Right. Okay. Still a bit weird, but all right, fine. I also don't see myself. So, okay. So yeah, I somewhat foolishly, long time ago, accepted this task to talk about non-equilibrium phenomena in quantum gases, but many body non-equilibrium phenomena. And it's basically like, unmanageable and uncoverable subjects for reasons that, at least that you might learn in this course. It's an unmanageable and uncoverable subject. So I have tried to make my life, somewhat easier by adding the second line of the title, which I don't see, but I think I know what I called it. Yes, okay. Yes, I'm going to focus on non-equilibrium phenomena in homogeneous quantum gases. And again, you will see what that means if it doesn't mean anything to you now. It's still going to be vast. And, a lot of it will, probably touch and repeat some of the things you've heard in other courses or will have heard in other courses. And, I will try to point those things out, but you can also, point out if you already know something or if you don't know something, and, please feel free to wave your hands as often as possible, and then you'll pass the microphone around or you shout. I hope we can make it semi-interactive, at least. So the problem that I'm facing, with this course, and the problem that we're generally, facing with non-equilibrium physics, but which is also part of its beauty, is embedded in this quote from Leo Tolstoy from about 150 years ago. All equilibrium systems are alike, and each non-equilibrium one is out of equilibrium in its own way. How many people recognize where this quote is from and what it originally was? How many people know the original? Wow, okay. That's not okay, right. So as you can imagine, Tolstoy didn't really say this. He was talking about happiness of families. He said all happy families are alike, and all unhappy ones are unhappy in their own way. Which is not to suggest that non-equilibrium systems are unhappy, but just to indicate this vast diversity, which comes as you can imagine for one thing, because every equilibrium system can be out of equilibrium in a million ways, right? Yes, it's a much richer world, but it's not just this sheer large numbers. So, there are more conceptual issues that we have to face when we deal with non-equilibrium many-body systems. And so somehow there's a dual purpose, I guess, to this course, and I don't know which one will in the end be dominant. I mean, one is to to illustrate where this diversity comes from and why it is a challenge for the kind of 21st century physics. But the other aspect of it is to sort of hope to show you that there is at least some hope to prove Tolstoy wrong, right? Yeah. So that it's not quite true that we have to think about every non-equilibrium system in a completely independent way and every time start from scratch, but that we're already making some progress, but there's also hope to make more progress to somehow provide some universal pictures, some classification of non-equilibrium systems. The quote, by the way, is from the beginning of Anna Karenina, as it says here. So if you haven't read it, you should. But it's not a homework problem, but read it at some point. Okay, let's see if I know how to flip my slides. Okay, I don't. Okay, fine. Great. Yes, flipped, right?
Perfect.
Yeah. Okay. Good. So yeah, it's a four and a half hour course, and so it's not easy to sort of to be aware of the red line that goes through it, which is why I want to start by giving you some kind of outline, but at the same time I don't want to fill this outline with too many details at this stage because it would not make any sense to you. Right? So this is just to give you the idea of what the general structure of the course is, and then after we actually go through at least some introductory remarks, we can flesh out this outline right here to see why it looks like this. So there's broadly three parts. And the first one is kind of motivational, and it should be less than this whole lecture. And it's, it has two subparts. One is on some general concepts and motivation, and the other one is to introduce a little bit, some some aspects of the experimental systems and the tools we are going to use. It is actually, it's primarily an experimental course, though. I try to point out to theory that we do understand. And this part will hopefully, be either familiar from your life before Lezush, or from week one and some courses that have already taken place or are taking place in parallel. And then basically, because as I said, it's a very rich world. One thinks of non-equilibrium phenomena as examples thereof. Okay, and so we'll go through various examples. About 5. They also have subsets among themselves. But you will see that for some reason they're kind of naturally divided into 2 parts. There's about 5 examples in total, but you'll see by the end of today, why I, at least semi-reasonably, try to group them into 2 plus 3, right? And what they are, you will know by the end of this lecture. Okay, everyone hears me well? At the back, you hear me well? And I enunciate reasonably well? I mean, you understand what I'm saying? Yeah. Okay, the people in the front. Anyways, there's spaces in the front. Oh no, maybe there isn't. Okay, it's all full. Okay, so I can't blame the people at the back for. There are spaces there. Okay, so the last row can always move there if they don't hear so well. All right, so let's start with this intro and some very general concepts in non-equilibrium many-body phenomena. Oh man, that's not flipping slides. What is flipping slides? This is flipping slides. Okay, fine. So this is a big word, that will show up a lot through this course and probably shows up in other courses as well. Universality, and this is also not a quote, which is not a particularly famous quote. It's just reasonably well put together first sentence of a recent paper from Eric Cornell, which says, physics has always been about explaining a lot with a little, which I agree with. And that's, closely linked to this idea of universality. But while this is, a big and popular word, we actually don't know what it means, in the sense that it is, at least in the sense that we use it in various ways, in various contexts, it will mean different things to different people. One thing that we know for sure is that, if you're writing, a paper or a grant proposal, you should always try to think how you can work that word into the title of it. But beyond that, it's a little bit mysterious. Right? So it means that that something is always the same. Okay, but there are different degrees of universality which we attain in different contexts. So sometimes it means simply that something is the same for different system parameters, say in equilibrium. And then in our context, we're talking about out of equilibrium, there might be also different parameters of the system and different initial conditions. That's kind of the lowest level of universality, and it's still often pleasing that at least that you can observe experimentally and or understand theoretically. And then a higher degree of universality, is if we can see that, seemingly different physical processes in the same system are actually fundamentally the same thing. And sometimes we achieve that. And then ultimately, what the hardcore theorists would call true universality, if something is really the same for seemingly disparate physical systems. Okay. And the different examples that we will talk about over the length of this course, these different degrees of universality will be achieved to different degrees. It's not always the same level that we attain. But it's a word to watch out for, in this course and generally in your physics life. So this is, having sort of introduced at least vaguely, this concept of universality, I want to stress how different, our state of understanding is of equilibrium and non-equilibrium many-body systems. So in equilibrium systems, we're very good at doing this, understanding that we can explain a lot with a little. And with very slight, simplification, very slight, slight of hand, and maybe slightly exaggerating, I want to illustrate this here on the left side of the screen. So, basically, like, if you sweep things a little bit under the carpet, then you could argue that the magnet on your fridge, or at least some brands of fridge magnets, are the same as the same thing to theoretical physicists, at least, as a Bose-Einstein condensation or Bose-Einstein condensate in a gas of atoms that you're here to mostly learn about. So I don't know how many people are familiar with this. How many people in the audience see this and say yes, of course? Hands up. Okay, good. Small number, yes. Okay. Yeah, it's good. I mean, you will learn more if you don't raise your hands to these questions too much, right? So I will go slower, but you will learn more. So it's good to just be honest, whichever way it is, right? Because I have no idea actually, even what age you are and how much you know. So here on the left we have a very simple cartoon of magnetism. Actually here what is drawn is a paramagnetic state, but let's suppose that this system could be ferromagnetic, so it could be fully ordered, right? And what you don't see or you don't think about if you don't stress it is that actually I'm not drawing a most general case. I'm drawing a so-called XY magnet or ferromagnet or paramagnet in this case, right? Which means that these little blue arrows, they're little spins and they can rotate only in the plane. Okay, so general Heisenberg case would be that they can rotate in 3D, but still it's not uncommon to have this kind of situation where they can rotate only in the plane. And here we have a high temperature state, which is paramagnetic, which means everything is random. There's no overall magnetization, and we also say that this state is symmetric, right? Which means if you twist your head one way or the other, it statistically looks the same, right? This will come up later in the course again. And then there's some low temperature phase where these guys are all going to order and they're all going to point in the same direction, right? And on the right hand side, we have again a very very vague, very crude cartoon of an atomic gas. Okay, so all these atoms, these wiggly lines, are represented by some waves, which have different wavelengths and hence, so let's say different phases. But one can not even talk much about the phase if they have different wavelengths anyway. And this is a thermal gas that I have drawn here. But a BEC is something where all these waves would have the same phase. Okay? And when I say they have the same phase, I'm implicitly covering the fact that they also have to have the same energy, right? Because they could not have the same phase everywhere if they didn't have the same wavelength, right? The same energy. So, superficially, these are very different things on the left and on the right. Okay, on the left we have some solid, we have some spins which are not going anywhere. They're fixed on the lattice, and all they can do is rotate. And on the right side we have a gas of particles which move around and have no spin. At least don't have to have the spin for this story, right here. And what happens to them with the lowering temperature also seems quite different. However, in both cases, I can represent the local order, say of this state by a number which goes between 0 and 2 pi. Okay. So on the left, I just have like the phase, the orientation of this of these little blue arrows, which is an angle between 0 and 2 pi, and on the right I have the phase of the wave, which is also an angle between 0 and 2 pi. Okay. And this is enough, for us, or at least for the theorists among us, to say that this is essentially the same thing. Okay, that these things, as we say, belong to the same universality class. Again, something that will show up probably in lecture 3 of this course again, in the context of dynamics of phase transitions, where we go, say, from paramagnetism to ferromagnetism, or from a thermal gas to a Bose-Einstein condensate. Right. So this is an extreme example of where we can explain a lot with a little. If you knew how to do experiments on a BEC, we wouldn't need to bother to do experiments on the X5 magnets and vice versa, because one is enough to understand the other. Now, in reality, what happens is there are some types of experiments that are easier to do on the X5 magnetic systems, and there's some other type of experiments that are easier to do on an atomic gas, and so you can combine this knowledge to have overall better understanding. That's in equilibrium. Right? Now, in comparison, this is what non-equilibrium many-body physics looks like, right? Yeah, somewhat cynically, right? We're making progress, but at least historically, this has been the difference. Right? On the left, we have something like super systematic, right? Yeah, with a few basic ideas we explain a lot, And on the right side, we basically have stamp collecting or butterfly collecting, whichever one is your favorite. So it's like it's super fascinating, it's super pretty. There's great diversity, but there's very little systematic approach to classifying these things. Actually, there's another quote I can throw at you. So Rutherford apparently a long time ago said that all science is either physics or stamp collecting. And actually, from today's perspective, we would say he should have said all science is either equilibrium physics or stamp collecting, because even non-equilibrium physics often looks like stamp collecting. But again, this is not to say it's bad. This is just the challenge we're facing, and we're making progress in trying to turn to make the right side look a little bit like the left side. All right. Again, I have to. Good. Okay. So for the purposes of this course, I have tried to come up with some classifications, right? And I failed. Okay, but I think it's still instructive to show you this slide. Okay. How we do, at least for the presentation for teaching students, how one could classify a different non-equilibrium phenomena, and there's at least 3 types of classification that I came up with, and my course is not going to follow any of them because none of them works perfectly, but still it's good to have this this slide in mind and see how every phenomenon I describe belongs in some way into the first column that you see, and then the second column that you're about to see, and the third column you're going to see in a few minutes later. So one way to say we have different types of non-equilibrium systems is by the origin of the non-equilibrium behavior. Okay, and this one I think I know how to do. I mean this one is pretty comprehensive, right? But not necessarily very insightful for understanding the essential physics of it. So these are I think 3 ways in which we can create non-equilibrium systems, and I think that any example like I run into I can put into one of these 3 categories. So one is that we have quenched something. How many people know what quench means? Okay, great. If I'm counting correctly, it's more than half. So anyway, it means change something too fast, right? So if you change something too fast and the system had no time to adjust, this is basically like flipping a switch in an electric circuit, and some capacitor was empty and now it has to charge, right? So the system is clearly not initially in equilibrium because you have changed something, but it might get there. Okay, that's one scenario. Right? That something just needs to equilibrate. In the most simplest case of like the capacitor is going to equilibrate, with some exponential approach in time to the new equilibrium state. Okay. And then another scenario in which we can have something out of equilibrium is that the system is continuously driven. So in this case, we cannot say like, if you just wait, it's going to reach an equilibrium because it is continuously driven. But nevertheless, it can reach some kind of steady state, which is not a thermal state, it's not a thermodynamic equilibrium state, but nevertheless, it might be stationary. So we will see examples of that later in the course. And here, actually, I think maybe I need to clarify and to make some distinction from other courses that you have. So driven can be at various frequencies. So, for example, I think Monica has Monica started lecturing?
Not yet.
Okay, Monica will start lecturing, and she will talk about some Floquet systems which are periodically driven. But there, she will be talking about very, very fast driving, right? Where the idea is that the system actually does not necessarily know that it's driven, right? So you're varying something so fast that you can integrate it out, but there's some static effective Hamiltonian that arises from the fact that you're actually changing something super fast, which is kind of an advanced concept. But actually, I just saw David leave the room. He was teaching optical lattices, and so actually this kind of fast frequency driving you do know about, or maybe you don't call it Floquet in this simple context, but it's basically the AC Stark effect. I mean, AC Stark effect is the simplest example of this kind of fast driving, okay, where you're driving something at 10 to the 14, 10 to the 15 hertz, right, at optical frequencies, and the atoms, the electrons know about it, but the atoms that we actually look at don't know, something is changing at 10 to the 50 hertz. They just see, that their energy is going up or down depending on how they move through some laser field, right? So these are very, very, very fast drivings, and that's not what I'm talking about here. Okay, here, we're talking about relatively slow drivings where the system does know that it is driven. The system, I mean atoms now, not the electrons, which know even about the AC starting point. And then the third type, which is neither quench nor driven necessarily, is some kind of intrinsic type of non-equilibrium behavior, which you can imagine happens if you have some dissipation. For example, the system is constantly heating from the outside, or is losing particles, or there are also some situations where disorder leads to such intrinsic non-equilibrium scenarios, or there's some so-called integrable systems where too many things are conserved, and so they can never reach equilibrium. So I think, even these three things are not kind of orthogonal axes necessarily. So for example, intrinsic non-equilibrium behavior might start at t equals 0 because I quench something. Okay. But still, this kind of covers, I think, the whole world of non-equilibrium system, but doesn't necessarily explain anything. The second classification I can come up with is that the non-equilibrium behavior arises in some contexts which physically seem interesting to study. And so one example, and this is not an exhaustive list, that's why we have 3 dots at the end, right? So already here, maybe I'm explaining a little bit more, but I have no hope to cover the whole world in a systematic way. But these are some that will actually show up in our course, right? And are kind of generic and I would hope self-evidently important. So one is the dynamics of phase transitions. It's a pretty dramatic situation where the system completely has to change its nature, such as go from thermal gas to a BEC, or from a paramagnet to a ferromagnet. Then if it has to do that in a finite time, it will always run into problems and get confused, right? So it's a problem where non-trivial non-equilibrium phenomena arise. Another context which is usually associated with driven systems is turbulence, which we will talk about it a lot, but I guess it's a word which is at least familiar in some very vague sense from everyday life. And the third category that I can think of and we will cover is closed quantum systems. So when you talk about equilibrium thermodynamics, then depending on what's your favorite ensemble to use for calculations, but you generally talk about a system which has the ability to reach equilibrium because it's coupled to some kind of bath, and it might be exchanging energy with this bath. Might also be exchanging particles with this bath if you talk about the grand canonical ensemble. And so it's a small system with a large bath, and that's how equilibrium. That's how we live with the idea that the equilibrium can be reached. But if you consider closed, isolated quantum systems, which is something that we can quite naturally create in quantum gases, and so all kinds of quantities are preserved, then you can probably immediately see that it's not obvious how the system can rearrange itself to reach equilibrium if it started out of it. And it turns out indeed that it is hard, and we will talk about it later in the course. At this point, you can see that I have 3 in the left and 3 in the middle, but they're not quite aligned, and that's kind of it's not just my PowerPoint skills, it is deliberately somewhat suggestive that in the simplest case you might think as critical behavior associated with phase transition dynamics being associated with quenches, because we go one way through a phase transition by changing something too fast, and or just at any rate. You might think of turbulence being associated with the driven system, and indeed it is. And you might think of intrinsic problems of equilibration associated with closed systems, and indeed it is. But at the same time, these things are not deliberately aligned because they don't actually always go hand in hand. So it's supposed to be a little bit suggestive for the beginning of thinking about these problems, but it's not actually universally aligned. And then I'm really retarded with this Zoom. Okay. And then we could try the most noble maybe but also the most impossible thing. But this is kind of where maybe we're going into the future, right? Which is to characterize non-equilibrium phenomena by how we understand them. So these are some advanced concepts that you may have heard a little bit about. And you will hear more about in this course, and they're so I put explanations in quotation marks, because they're kind of at least temporary, remedies, right? We say like we understand things, then we can somehow connect them to one of these concepts like turbulence, non-thermal steady states, pre-thermalization, non-thermal fixed points, dynamic scaling, or universality far from equilibrium. These are sort of big words, that are showing up in current research, and we often say like, oh yeah, that's like one of these things, but it doesn't actually mean we understand it in the way we understand equilibrium physics yet. Okay. All right, and here, here the list could really go on. And one thing again, which is not a mistake, I did it on purpose, and it sort of illustrates. Well, can somebody see something wrong? Actually, I should ask. Can somebody see something wrong, something odd about this classification into 3 categories? Anyone? Is there something stupid that I did? Come on. Don't need to know physics to spot that something is stupid. Guys. No? Nothing wrong? These are supposed to be 3 orthogonal ways, 3 different ways of classifying things. Just by looking at the words like a crosswords. Yes?
You have turbulence in 2 classes.
Sorry?
You have turbulence in 2 classes, right? If they're orthogonal. Shouldn't be.
Good. Yes, I have turbulence in 2 places, right? I think that's what you said. Anyway, you mentioned turbulence. And that unfortunately is not my mistake. It is the sad state of affairs. Okay. It sort of illustrates where we are with understanding non-equilibrium systems. That on one hand, we're studying turbulence as the phenomena. And on the other hand, very often when we try to understand a non-equilibrium phenomena, we say like, okay, we got it. It's just like turbulence. And that's a cop-out because we don't understand turbulence itself. So often we will say like, by recognizing some similarities, we will say like, oh, wow, okay, now we understand it. It's a bit like turbulence because that's our job in that paper. But then there's a host of other literature where we're admitting that we actually still don't understand turbulence and we're still trying to understand what it's about after hundreds of years of thinking about it. And so indeed, you will see turbulence show up a lot in this lectures, right here, but sometimes it appears as explanation and sometimes appears as a problem. Right? So it's just some kind of, it's basically something that is defined as a negative. It's like either we understand it or it's turbulence, right? Or you can say that, there's human knowledge and then there's turbulence, right? It's the opposite of what we know how to understand at the microscopic level. And so as I said, like, this slide, I want to burn into their minds. Actually, I don't know, Tomas, do they get the recording of this or do they take notes? Or how does it work? Or do they get slides?
They will get the slide if you give them to us.
Okay.
And they take notes, yes. And
okay,
it's
fine,
also recorded. You also record
okay, but it's not easy to take notes. So try to take notes, I guess, a little bit. So I want to burn, kind of this slide into your minds. Even though, as I said, like, I will not follow any of these classifications throughout the course because it's impossible. But still, it might be a fun kind of, bingo for you. When you see an experiment to say, like, this is like a driven system related to phase transition dynamics, and the explanation has to do with non-thermal fixed points or something like that, right? Like, to see with every phenomenon you encounter in this lecture or otherwise, you can see whether you can find where it falls under these 3 different categorizations. Okay. And then, I already admitted that I'm not covering everything, but there's things that I'm not even trying to cover, okay, but which might come up in different courses. So as I said, I'm going to limit myself sort of generic problems in bulk systems, in bulk homogeneous gases, which means I'm ignoring all kinds of things. I'm not even trying to touch on various things that happen, for example, in lattices, which maybe is covered a little bit in David's course, maybe is covered a bit in Monica's course. Maybe some things will be covered in Thierry's course as well, I'm not sure. So there's a bunch of other big words, like light cone dynamics, many-body localization, quantum scars, or time crystals, which will not show up in this course. But still, it's good to mention them so you just know that more stuff is out there. Okay, so that's our first part on the general flavor of things we're going to look at. And then part 1.2, according to the advertised outline, is to tell you a little bit about the experimental side. So what kind of systems we're dealing with, and what kind of tools we're going to apply to them in order to study non-equilibrium physics. And this will hopefully overlap a lot with the other courses, but at the same time, it's generally stuff that bears repeating. Right? So, I mean, since you're here, you probably already bought the pitch that quantum gases are cool, and they are. But in this particular context, what we like, also it's true for equilibrium, but it's even more true for non-equilibrium. What we like is that they're dynamically tunable. Okay, so you have probably heard, and you will hear again and again, that various parameters of quantum gases are easy to vary. Okay, but in our context, we just stress additionally that they're easy to vary dynamically, and so that makes it easy to induce non-equilibrium dynamics. The other big issue is that the sales pitch for this field, and why for non-equilibrium they maybe have even more competitive advantage than for equilibrium physics, is that everything is slow. Okay, so so the atoms are heavy compared to electrons, and also the energies and temperatures are much lower in quantum gas experiments than in solid state. And so in the end, things that happen in solid state on maybe picosecond and femtosecond scales, in our case, happen on microseconds, milliseconds, or sometimes even second scales. Right? And so all kinds of things are, real-time resolvable. You can induce a non-equilibrium phenomenon and then study things in real time, which is solid state. Actually, in the last 10, 20 years, there are examples where people are trying to do that, and that's very cool. But historically, it's much harder. They're usually basically measure only equilibrium. But you change something, and then the system settles before you can see the dynamics of the settling into the new experiment, into the new equilibrium, and you just see the new state that you have. And then finally, not only is it generally resolvable because it's microseconds to seconds, but also we can change the speed of the dynamics because we can tune the interactions in the system. And Thomas warned me that actually you don't know about it, so I will tell you a little bit about it in the next few slides. Right here. But generally, you've heard things are very tunable, and that basically means we can tune both the potential energy term in the Hamiltonian and the interaction energy term in the Hamiltonian. If you can tune those two, then you can tune everything because that's all there is. At the level of the microscopic single particle Hamiltonian, so you can change the potentials that the particles move in, including the dimensionality that they move in, and we can also change how they interact with other particles. Okay? We cannot change the kinetic energy term, which is just the mass. Right? We can in lattices, I guess, just to not confuse you, in what David was talking about, you often talk about the effective mass changing, but that's because you're actually tuning the potential energy term by putting the atoms into the lattice. Okay, so that is very general pitch for the field. Now, in our case, this is less obvious that you know about it. We're going to talk about homogeneous quantum gases in so-called optical boxes, because that's going to simplify our understanding, and not just for the purposes of this teaching, but for our experiments, it has generally made things more viable to both perform and understand. So, again, I need to calibrate where we are standing right here. So I wrote here homogeneous quantum gases in optical boxes, as opposed to harmonic traps where we rely on the local density approximation. So to how many people just the title and the subtitle of this slide makes sense? Not so many. Okay, great. Okay, fine. I mean, it's good to know either way. So it seems to be less than half. So I should say a little bit about it, though this is not the course on it. So traditionally since 1995, right? People have been making these quantum gases in harmonic traps because that's technologically the easiest thing to do. It's the most natural thing to do because if the trap has a minimum, that means there's no first derivative of the potential in space, and then the leading order term is the second derivative, and the second derivative is the leading order term. That means the trap is approximately harmonic. Okay, so almost everything you make that has a special point where there's a minimal potential energy is to some level of approximation a harmonic trap. Okay? And we've all been making this, and we still do for the past what is it, 26 years now. And that's great. They're beautiful traps. but to interpret the experiments in these traps, you need to invoke the so-called local density approximation. Okay. Now, the local density approximation means that basically you look locally, okay, and you locally have some density, right, and temperature, whatever you can define locally to some degree, and then you assume that the local behavior is the same as if you had an infinite system with that density, that temperature, and whatever other parameters are needed to describe the system. Okay. And then as you move to a different point in the harmonic trap, you assume that is again true, right here, though with a different density, but not a different temperature, right here. So additionally, what you usually have to assume in a harmonic trap is that these different parts of the trap are also in equilibrium with each other. Okay. Which means that when you add up the local chemical potential, which is defined from interactions, temperature, and so forth, and the external potential, it adds up to the same thing everywhere in the trap. So there's nothing wants to flow. It not just doesn't have time to flow, but nothing even wants to flow. The total chemical potential is the same everywhere, and the temperature is the same everywhere. And that's, it's a somewhat constraining assumption, but most of the time it's okay, right? And when it's okay, then the harmonic trap even have various advantages, even though they don't match what is in books on many-body physics, right? So since many-body physics was invented, the theorists always assumed that it was a homogeneous system, right? And a lot of the conceptual things that we want to understand in the simplest possible setting, are based on bulk homogeneous gases. Now, in the harmonic traps, a lot of the time it's okay to use this LDA, right? And basically study bulk systems using homogeneous traps, But sometimes it fails. Sometimes this approach fails, horribly, and so there has been a motivation in the field since the beginning, to also create actually homogeneous samples which have uniform density, throughout. And this has, happened about, again, it's not a course about that, but it has happened now 7 or 8 years ago, and it's kind of a mini trend. It's still a minority of the experiments in the world that are using these homogeneous box trap gases as opposed to harmonic trap gases, but it's a growing trend, and for some type of research, it is very advantageous, and it's particularly advantageous for non-equilibrium studies, as I'm going to tell you a little bit more in a moment. Okay, so that's just a basic background. But in some sense, if you didn't know anything about the experiments, you might have even assumed, that the systems are homogeneous, right? Even though they're not. So this is just basically realizing what in books and undergraduate courses is always assumed anyway. And there's a review on that three of us wrote recently. It's literally just weeks old. So if you're interested in this beyond the context of non-equilibrium physics, you can read that. But I don't want to spend too much time on it. Right, so the gas is homogeneous, and we make it in this optical box, and this is here on the left is the cartoon of what we mean by that. So these gases are really in boxes in a very classically, intuitive way. So they're not drawn to some minimum of a potential of a trap, right? They're just in free space, but they're confined to some region of free space with some repulsive walls, okay? Which in classical world might be cardboard. In our case, it's blue-tuned lasers. Okay? And so here on the left, we have the most commonly used 3D box, which happens to be cylindrical in shape just because it's easy to make. So it consists of this green laser tube, right here, and just 2 end caps. So it looks like a Coke can, if you like. And then sometimes you also want to study low-dimensional systems, and that will also show up later in the course. And if you want to study a low-dimensional system, not just for homogeneous, but also, this is true for harmonic trap as well. What you do is, where's my mouse? Here. What you do is just, you squeeze the gas strongly along one direction. And you can squeeze it along 2 directions, and then it will be 1 dimension. Okay. And what we mean, sometimes people ask, and rightly so, what we mean by 2-dimensional is not that there is no thickness, because of course there is always thickness. What we mean is that the gas is kinematically 2-dimensional because by making the confinement very tight along one direction, you have very widely spaced discrete quantized levels of single particle states along that direction. And then if the spacing of those levels is larger than any other energy in the system, then the atoms are confined to the lowest state. So there's no dynamics along that direction. They just, if you like, if this confinement is harmonic, they're just confined to the lowest state that has energy half h bar omega z. This is the z direction. And it's the same thing, by the way, for in solid states for 2D electron gases. They also have a thickness. They just don't have enough energy to move out of the lowest state along that particular direction. Anyways, so that's all I have time or want to talk about boxes. We can talk about it afterwards if there's some way to discuss, or you can read about this here. And the reason this took a while to develop, so it's only 7 years old, not 25 years old, is that it was greatly facilitated by some advances in shaping of the light, so we can actually configure these things the way we want. Right? Again, not the course about that, but you can read it about it elsewhere. One uses, I will have one slide. One uses something called the liquid crystal SLMs, which you print a phase on a laser beam in order to sculpt something in the Fourier plane. It's basically holography, or so-called digital mirror devices to simply, create configurable masks in order to project these kind of traps onto the atoms. Or at some point, when you know what you're doing, you can just use some fixed optics. Once you've explored and figured out what you want, you can even use fixed optics to get one particular kind of box trap. Now, in the interest of your general education, before we go on, I know that David has just left the room, right? But still, I would like a poll on this as well, because it's maybe more important to learn basic physics than advanced physics. So, how many people in the room know that blue detuned laser beams are repulsive to the atoms?
I guess all.
How many don't know? It's hard to count. It's easier to measure around 0 than around 100%. Okay, nobody who doesn't know. Okay, how many people see that is conveyed in this classical drawing on the right of ball on a spring under gravity? Who is the one person on the right? The camera just shows me the arm, but not the person. Okay. So let me tell you a little bit. It's a digression, okay, but maybe it will make you understand better the AC Stark effect, right? So what we have here is familiar, right? I think everyone knows what is drawn here. I just know how it has to do with the green lasers. So what we have here is ball on a spring, and then we add gravity, and the ball sags, okay? And so we have a quadratic potential half kz squared, right? The spring, right? And then we have the gravitational potential minus mgz, okay? And we can complete the square. And we see that this is again a harmonic oscillator, but it's oscillating around a different equilibrium position. That is very familiar. What might be like, just slightly less familiar, you might have forgotten it, but you could quickly recover it, is that by going down in the gravitational field, the ball, so this is not a ball, it's a cube, okay, but I always say ball on a spring. This cube lowers its energy, okay? So the frequency of small oscillations around the new equilibrium is the same as before, but the absolute minimum here in the solid black line is lower than in this dashed parabola, right? And if gravity was upwards, I didn't want to do that, okay. And if gravity was upwards, then the ball would move up and would have a local minimum in a very symmetric position on the right. And again, this minimum in absolute sense would be lower than the original minimum without gravity, okay? So maybe you don't like to think about gravity going upwards, but you can just imagine a ball on a spring. I hope you can see this. I know I'm in a small screen. Can you see when I do something in the small screen with my hands? Reasonably? Okay, fine. So here it's easier to imagine I can apply a force to the right, my right. Okay, that's your left. And the ball will move there, okay? And if I apply a DC force in the other direction, the ball will move there. Now, this is because ball is smart, okay? So if you apply the potential gradient, a force in one direction, it goes there. That's a smart ball. Okay. Now, as long as now imagine I'm not applying a DC force, but I'm slowly varying the force. It's a sinusoidal oscillation. Then the ball will still be smart. Okay, it will still oscillate in phase with the force. And at various times, its potential energy will be more or less lower than the original equilibrium without a force, but always lower, right? So we average over the period, like on average, the energy of the ball will be lower than if I was not applying the force at all. However, what happens if I increase the frequency of this oscillation above the natural resonance of the ball? Can anyone tell me? Come on. What does the ball do if I drive it force above resonance? Yes?
It'll move out of phase with the force.
It oscillates out of phase. Okay. So the ball becomes stupid. Okay. Right? The gravity is downwards, right? But the ball moves up, right? And then you're like, okay, ball, you're stupid. I'm going to help you. I'm going to turn the gravity up. Okay. But the ball is so stupid, it actually starts moving downwards, right? And so when the ball gets stupid and moves out of phase from the force, then its energy is, for the same reasons as drawn here, its energy is always higher than the original energy without the applied force. And then you can average that over the period. If you get some average, doesn't matter, but the sign of the average is predictable. Okay. And so because of its stupidity, it's bad for the ball to be in the field where things oscillate above its frequency, and it's good because it's smartness. It's good to be in some field where things oscillate below its resonant frequency. Okay. And this is why the AC Stark effect changes. Okay. It's the electron that is smart or stupid, right? Or the polarizability of the atom. And I'm sure David has derived this in all kinds of ways, and you know it for a fact. There's like 1 over delta, and so delta is going to change sign for the AC Stark effect. But this is the basic reason for it, right? That if the ball is too stupid to follow, too lazy, whatever you want to call it, then its energy is actually higher when the oscillating force is present. And then once we know that there is an increase in potential energy at high frequencies and decrease at low frequencies, then David told you, I guess, if now the intensity of the laser field varies in space, that turns into a trap. That turns into a trapping potential. So you stay away from the regions of high intensity blue lasers, and you like to go to the regions of high intensity red lasers. Right. Okay. So that's again a digression for general education. And whenever we find that there's some general education that could, use supplementing, we can stop. Right. We have time. So blue lasers repel, and then if additionally we know how to shape them using these fancy things, then we can create literal boxes, right? For the atoms. The atoms are here in blue, by the way. I actually have said it in the beginning, but that's obvious. Now, not to lose track of our story right here, which is the many body. Sorry, one more slide. So this has been done. Again, you can read this in the review. It has done for bosons in 3D, bosons in 2D, bosons in 1D. Actually, there's no fermions in 1D, and there's a reason for that, and why that's harder. But it has been done in various dimensionality for various kinds of gases, including molecules. Right? Again, not the course about that, but there's a recent review you can read. But conceptually, for where we are going with our attempts to understand non-equilibrium physics, there's specific reasons why we want to use homogeneous gases. One is like, for example, these are just examples. We're going to look at these phase transitions, as you will see during phase transitions, the correlation in the system diverge. The system becomes correlated over very large distances, and that's where local density approximation fundamentally breaks down. Okay, because one can see that pretty easily, I think, because if you sit at some point in the trap and you say, I have this density, I have this temperature, and you can calculate what the correlation length should be, right? And you get some number, 10 microns, okay? And that means 10 microns away, I can predict exactly what's going on, right? Because you're assuming you're in a uniform system, right? But then you go 10 microns away and actually everything is completely different, right? Because 10 microns is actually a huge distance for this harmonically trapped gas. And the correlation line you have calculated is itself not equal 10 microns away. It's not equal to 10 microns away. Right? So you run into obvious inconsistencies if you try to apply local density approximation to something which is correlated over large length scales. The other reason that these homogeneous systems are going to be better for our non-equilibrium studies is that, as you will see, there's some things that naturally happen in momentum space, right? At least the theory has been developed in momentum space, and it's natural to think about them that way. Right? And so in a harmonic trap, the real space and momentum space are equivalent, right? They're both interesting if you like, but neither one is pure because plane waves are not the eigenstates of the system. Right? Whereas in a box, the real space is kind of trivial, because it's all the same, but the momentum space is cleanly observed. Right? And then finally, another reason that the homogeneous systems will be advantageous for our specific purposes in this course is that sometimes you have very fast local processes which are density dependent, okay? And then you're really in trouble, right? Because then in order to, if you have a homogeneous system, and you have some heating or loss or whatever kind of process, that is strongly density dependent, then it doesn't happen in the same way everywhere in the trap. And you would actually have to have mass flow in order to reach global equilibrium and for your global measurements to make any sense, but there's no time for that. And so the only way to see those things cleanly is to have a homogeneous system where everything happens the same. Even though it's independently happening in different parts of the trap, the same thing is happening. All right. Any questions at this point? I guess I should also sometimes ask that. No pressure, but certainly no fear. No? Okay.
Seems fine.
So, we're still not there, okay? Because again, I sort of cannot resist teaching some little bits of knowledge, if not wisdom, that are related to things we talk about before we get to the main story. So I said I don't want to talk too much about how we make boxes and all the non-equilibrium reasons that they're good for. But I want to point out one thing which I found amusing when I understood it for the first time, a few years ago. So a lot of these box traps, but more generally, like arbitrary trapping potentials, which would be good for all kinds of things, lattices or whatever, for all these other courses that you're hearing about. Often the slide shaping is based on some kind of holography, right? So again, this is some so-called spatial light modulator, which is basically a liquid crystal. With every pixel, you can control the index of refraction. Right? And so if you reflect some laser beam of this screen, if you like, with the spatially varying index of refraction, you imprint some spatially varying phase onto your laser beam. Okay, and then after some propagation in the Fourier plane, this phase pattern results in some intensity pattern, which is what you like. Right? It's a beautiful concept. Right? However, if you think a little bit about it mathematically, like it's not possible to do whatever you want, right? Because you don't have enough degrees of freedom. Okay? So if I start from the other end and say like, I want to create this light intensity, okay, and a Fourier transform to see what I need to impose in the Fourier plane, I will generally get some complex function which has both variable amplitude and variable phase, right? So I actually need control over both in order to create the pattern that I want, but I don't have it. Okay? Even though there is a separate device which controls the amplitude, so in principle you could align the two so that in series you control the amplitude and the phase. This is a pain in the ass, and that's not what we do. Okay? So generally we use both amplitude controlling devices and phase controlling devices, but so far we have not tried using them in series in order to control both. Yet the field is very successful. And the reason it is successful is that it turns out there's something called phase dominance in digital holography, at least something I call phase dominance in digital holography, and probably others too, right? But it's just not an official name that I'm aware of. So I want to illustrate this here for you as part of general education with these two pictures of Einstein, okay? One is happy, one is sad, okay? And which one do you think is going to win in the end? Which one is going to win it's going to be a battle. Which one is going to win, the happy or the sad?
Happy.
Louder. Come on, it's 50% chance. It's good odds.
Happy.
Happy, good. Happy is going to win in the end. So these are pictures, two pictures of Einstein, and these are real pictures, right? Okay. I mean, real in a mathematical sense, right? They're also real pictures, but they're real in a mathematical sense. So here in the front, we have the amplitude of these pictures, and in the back, we have the phase, and the phase is uniform, right? It's all real field. Okay? And then I can Fourier transform this, right? And this is what it looks like. This is genuine, right? I'm not making this up, okay? This is the Fourier transform of these pictures. And now, again, in front, we have the modulus, right here, and in the back, we have a phase, which is now quite intricate, right? And so if I Fourier transform this back, like of course I will get the real thing right here. But again, I don't have the freedom, to control both the amplitude and the phase. So it can be hard to get either happy or sad Einstein. But the way I want to illustrate that the phase dominates in this business is I'm going to do something preposterous. I'm going to take the amplitude of the sad Einstein and the phase of the happy Einstein. Okay, mathematically I know how to do that, right? And so this is nonsense. Right? This is not the Fourier transform of anything, right? I mean, anything sensible. But if you do take this complex function, and as somebody already guessed, and Fourier transform back, it is essentially happy Einstein. So you can attach almost any rubbish amplitude, to the correct phase pattern, and you will get something which captures the essence of the field that you want to create. That's a complete aside on digital holography for light shaping. But there's something else I want to tell you before we get to non-equilibrium still, which is about this BC in a box. Again, we don't want to spend the course on it, but there's a few things that you're going to need later. And also these are good places to sort of to make you think, do I understand this? And go away and maybe do a little bit of calculation between the lectures and so forth. So the first thing we need to know, because you will be seeing pictures like this throughout the course, is that if you take this BC made in a cylindrical box, and do the so-called time of flight expansion, which I'm sure you have heard about in some course before, I don't have to ask that, then it expands like this diamond, okay? This is not a trivial problem. I mean, numerically it's explained. There's some intuition for why it does that, right? But it's not something that, in terms of differential equations, it's not something that is actually analytically fully explained, right? But anyway, that's what it does. So you can tell, that it's something is interaction dominated, that is essentially not temperature, right? It's not thermokinetic energy, then it expands like this. And if you're not that cold, so this is essentially 100% condensed fraction. If you're not that cold, so you kind of 50-50 condense, say, then you see here BC in the center, which has a diamond, whereas the thermal gas, which is dominated by kinetic energy, expands completely isotropically. Right? It doesn't care about the shape of the container it came from. Okay, and from by looking at the pictures like this, the one that says thermal and BC, one can deduce things like the temperature and condensed fraction and so forth, similar to harmonic traps. And the critical temperature, right? So you can see when this diamond first appears or disappears, that's the critical temperature for condensation, or the critical atom number at a given temperature, depending on what you keep constant. Okay. And so it's important to recognize these pictures. When something is in order BC, it's a diamond. Okay. The other thing that will be important for our little calculations that I will either do for you or ask you to do in your head or ask you to do between the lectures is that one way you see that you're in a box is that you just measure the critical atom number for a given temperature, or you could invert this around just by flipping the x and y axis and measure the critical temperature for a given atom number. And so in the conventional static harmonic traps, the critical atom number scales as t cubed, whereas in a box it scales as t to the 3/2. So again, I have to ask, how many people are familiar with these results, with these scalings? 80%. Okay, good. That's not bad. But again, if you're not, no shame. But but you should do this for homework until the next course. So as a reminder, this is the basic idea. The number of atoms you can have in the excited state for negative chemical potential is just some integral of g of epsilon d epsilon with Bose occupation number. And then if mu goes to 0, that tells you what's the maximum you can fit. Was maximum number of thermal atoms you can fit into a gas at that temperature, and hence that's the critical atom number for condensation, and that's just this integral. And then if you just know the shape of the density of states, so in 3D harmonic oscillator it scales as epsilon squared. If you don't know this, then figure out to derive it for homework. That gives you NC goes to t cubed. Right? And in a 3D box, this is an easier calculation. The density of states goes as root epsilon, which is like what you learn in your solid state courses, right? And so just plugging in these scalings into the black equation on the left, you get that one is t cubed and the other one is t to the 3/2. We will need this t to the 3/2 in order to explain some non-equilibrium phenomena that we're going to see in a moment. Okay. Another question. Good. This is also to test both the electronics and our ability to communicate. So, if you understand the basic Bose-Einstein condensation, which is the input for what we're going to do later on, here's a genuine quantitative question. So in some trap, the BC critical temperature, the critical temperature for quantization for 1 million atoms, and they're non-interacting spinless bosons, the simplest possible case, is 400 nanokelvin. Okay? Now suppose in that trap, you have 2 million atoms at 400 nanokelvin. The question is, what is the condensed fraction? I'll give you a minute to think. And then I don't know how we're going to communicate. I asked this at Lazush once before, and then they just raised pieces of paper with 2-digit numbers. But I'm not sure I'll be able to see it now. So, Thomas, what do you suggest? Do they raise hands? Do they? In any case, I'll give you a little bit of time for everyone to calculate themselves.
Pick up a random student and ask him.
Sorry, what?
Should I pick a randomly student and ask him?
I can randomly, I don't know how to point. I mean, I think if a point's not obvious where I'm pointing. Well, let's wait. I think it takes a moment to get your head around. How many people have an answer? Okay, so we wait more. Does anybody want to ask a question because they feel that something's missing? Sorry, do you want to give an answer or to ask a question? Huh?
I thought you were asking for the former.
Sorry, what?
I thought you were looking for an answer.
Well, I don't want, if one person just gives the answer, then I don't know how many people got it. So first let me see, does anybody have a question? Does anybody have a complaint? Some information is missing, maybe. No, nobody has a complaint. Okay. So how many people have an answer? I'm not going to ask you what it is. How many people have an answer for themselves?
Not much.
How many people would want, okay. How many people would like more time in order to get an answer? Okay. You would like more time? You would like more time?
Very little bit.
Okay, fine. Then let's wait a little bit.
A little more.
Because if people are not trying, I don't want to wait. But if people are trying, I'm happy to wait a bit.
The question is if his graph is harmonic or not.
Sorry?
I'm not sure, but it depends if the trap is harmonic or not, or?
Okay, so that's a very good question. Yes, so it's good to raise that question. And it's deliberate that this is not said. Now, this is a hint of how the answer depends on what kind of trap it is. You could use your favorite trap to calculate if you wish. But the answer is the same for any trap, which is a hint that there should be a simple way to think about it. But also that you can use any trap to calculate the answer. You know, if I was there, it'd be less awkward, the silence, than this way remotely. But honestly, like, if you spend an hour of your life understanding this question, it's an hour, well spent, right? So silence is a bit awkward, but like, yeah, it's totally worth an hour, this question, right? If you just don't want to give it that much because it's practical. And I see some discussions going on, which is also good. How many people have an answer now?
Okay, raise your hand if you have the answer. They are still discussing.
Actually, I'm going to maximize you. So let's see, I try to read the faces. So how many people have an answer? Hello? Okay, it's growing a little bit. But probably we should reveal it.
I think most of them know the answer, I think. Or at last.
Tama, what are you saying? Should we reveal the answer? Yeah, don't give it to the first guy. That's too easy.
Okay, I'm not really sure if I don't know. I feel a little
Good?
uncomfortable saying this, but okay, it seems like you would say the condensed fraction is half, right?
I don't hear it at all somehow.
Okay, maybe. Can you hear me now?
Yes.
Okay. So it seems a bit like a trick question, right? But so if you would assume that the critical number is 1,000,000 at 400 nanokelvins, that any number of atoms that exceeds 1,000,000 would condense into the condensate, right? So you would say that in the end, for 2,000,000 atoms, the condensed fraction would be half.
That is correct. The condensed fraction is half. Did everyone else who had an answer got 50%? Yes. Okay, good. Good. And so, but it is instructive, it's good for the soul to also waste time and go through the process of saying like, TC goes as like n to 2/3 or n to 1/3, depending on the system, and then see how TC changes, and then get the formula 1 minus T over TC cubed or whatever it is depending on the system, and run in circles, and you'll get the same answer whether you do it for the harmonic trap or for the box, right? Or for any other trap, right? Okay. But the essence is actually to understand that none of that matters. That what Einstein's calculation actually tells you, and that's why you're going to be able to now answer the next problem that's going to come up. What Einstein's calculation tells you that at a given temperature, there's so many you can fit into the bees, into the thermocloud, and everything else goes into the bees. Okay, the answer is 50%, and if you're not sure, if you didn't get it now, that's fine. But try to think about it before tomorrow. What was that?
Question from the
Just
back.
waving. Okay.
So I'm not sure, but I thought about it a bit another way. I mean, if you would fix the trap, if you would say you have an harmonic trap experimentally, and the trap depth basically in an experiment defines your temperature. And if you now increase the number of atoms you have, then you increase the density. And if you increase the density and you get the condensate, obviously, if your density times the de Broglie
I'm
wavelength.
sorry, I can't follow. Can you? I don't know what to do. I hear every other word.
Okay. Maybe
I know you're in a harmonic trap, and you said something about trap that controls the temperature or something like that.
Yeah, exactly. And if you now keep the same trap, since the temperature is equal, then you increase your density of atoms inside the trap, or? This is the way I thought. So far you...
Well, actually in this scenario, you increase the density only at R equals 0, but because everything goes into the condensate, but yes?
And my thought was then you increase your phase space density. And if you increase your phase space density, it's kind of changes your critical temperature, and that would mean that it will fully condensate. Or is this wrong?
I'm not sure what you said, but I'll say what is the truth. Okay, if you increase the atom number, it changes the critical temperature. That's one way to get it. Okay, so as I said, like the critical atom number goes as T cubed or more. What the way people usually derive it for you, even though it's not so helpful, is that the TC goes as n to 1/3. Okay, and so I said like, oh, TC is 400 nanokelvin for a million. Now it's 2 million. Let's raise 2 million to 1/3. So just need 2 to 1/3. Okay. And so TC is going to be 400 nanokelvin times 2 to 1/3. Okay, that's TC. But T is still 400 nanokelvin. Then you find another equation that they gave you, which is the condensed fraction is 1 minus T over TC, everything cubed, right? And then you plug in, that your T is 400 nanokelvin, but your TC is 400 nanokelvin times third root of 2 into this equation, and you get 50%. And then you can do the same thing, with the power law for the box, and you're like, oh shit, that's the same. How come, right? And then you come around to understanding it's actually better to think at fixed temperature, increasing the atom number, and everything that is once you have saturated thermal cloud, everything has to go into the condensate.
Okay, yeah, thanks.
I don't know if that helps, but I'm about to show you the experiment, which was understood. I hope I'm going to show that today. Otherwise, I'm not doing so well with time, but it's good. It's good. I'm going to show you the experiment where this understanding actually led to like this last decade's paper. Just by understanding this kind of stuff. It's going to be our first story. Oh no, okay. I have the crash course in interactions. I forgot about it. Maybe I'm not going to show you the experiment today then. Right. So yes, I was asked by Thomas that actually some stuff about interactions was not covered. So I said we can tune the potential, and we have learned now that there's these things, homogeneous traps as opposed to harmonic traps, but also we have seen an example where some calculations are the same in the both, right? Or give the same results. Some essential physics is the same. But boxes are good for various non-equivalent things we will study later. Now the other thing we can tune is interactions, and Thomas warned me a couple of days ago that this has not been covered in other courses, and so I tried to include something, but I didn't read his email carefully, so I included more than he asked me to, but it's still only a few slides, and again, it's stuff that bears repeating. This is going to be very sloppy, just for intuition, and here are some references to more professional stuff. So generally on collisional dynamics of cold atoms, there's an old summer school notes that was written by Jean Dalibard. It's at this website, but you don't have to copy the website. You can just Google, Jean Dalibard collisional dynamics, and you'll get it. And then there's a review of modern physics, a so-called Feshbach resonances, which will come on this last slide of this section. So about interactions and how we tune them, which will be important for non-equilibrium studies. So we have these neutral atoms, okay, and they interact via van der Waals potential, which I sketched here. So there's some short range repulsion at the range of the Bohr radius. This is like when the electron orbits actually start to overlap. The minimum of this potential, which is basically the size of the molecule, is, I don't know, a few A naught or 10 A naught, I don't know, it depends on the molecule. And this depth is, some electron volts, right? Because combination of electronic orbitals that make a molecule, reduce the energy by some fraction, 30% of the usual electronic energies. And then at very large distances, this is R to the 6 potential, which I'm sure you were told many times before, comes from induced dipole-dipole interactions. Your usual dipole interaction will be 1 over R cubed, but because the dipole itself is induced by fluctuations, you end up with 1 over R to the 6, with some coefficient C6. Okay. Now, the first thing that will be important for us to understand is how long range these interactions are. We call them short range, okay, but it has to be some range. I want a number in meters, okay. And since this C6 divided by R to the 6 is a power law, it doesn't naturally have a length scale. But as often we do this dirty trick in physics, we have only two kinds of terms in the Hamiltonian, the potential energy and the kinetic energy. And so we can just balance them out, or you can call this dimensional analysis, to figure out some characteristic length, associated with this potential, right? So this range of interaction I call B here, okay? And if I just equate some kind of kinetic energy, right, to this potential energy, I get that B is 4th root of mc6 divided by h bar squared, which turns out, it's not obvious at all, it depends on various microscopics, but it turns to be of the order of 100 Bohr, okay? And we call this short-range potential. We call it short-range, because it doesn't have effect at infinity, if you like, but actually the number is also quite small. Right? So if you compare this with some relevant numbers, which are the thermal wavelength and the distance between particles, they're both much larger. Right? If you have, typically the condensation happens at something like 10 to the 12, 10 to the 13 particles per centimeter cubed, and I guess you have learned in some course by now that the thermal wavelength is similar to the distance between particles at the condensation. That's how the degeneracy is defined, right? When the wave packets start to overlap. Right? So lambda here is thermal wavelength, h over root 2 pi mkt, and d is the 1 over 3rd root of the density. And both of those are something like 10,000 Bohr radius in a typical experiment. Okay, maybe there are 1,000 in some, but they're always much, much bigger than B. Right? And so, in very loose words, if B is much smaller than both lambda and D, then we have a dilute gas, and the particle interactions are only S wave. Okay. Again, you notice dilute is, I guess, intuitive, right? So basically, these guys are 10,000 A naught apart on average, right? And only when rarely they get within 100 A naught of each other, they actually interact, right? So you can see how that doesn't happen often in some sense, right? And the other part, from your basic courses in waves and first course in quantum mechanics and so forth, when you do some kind of scattering, say X-ray scattering to probe the materials, or like whatever they do at LHC and so forth, you know that in order to probe the structure of something, some length scales, right, you have to send in some probe particles which have a wavelength shorter than that, right? And so here we have particles, atoms, which have a wavelength much larger than the range over which this potential varies, right? And so these particles cannot gain any insight as the scatter of such a potential, i.e. another particle. They cannot gain any insight into the details of the structure, right? So all they see is some blur, right? Which is hence fully symmetric to it's just smeared out into a little small sphere, and so you get only isotropic scattering, what we call S-wave scattering. And so, without being very proper, this intuition that we have dilute gas and only S-wave scattering at low temperatures that we are interested in, we model this potential with some delta-like potential of some strength, right? So U of R is U naught. Delta of R is the 3D delta function, which means that it has units 1 over meter cubed. And so, for example, mean field potential in a BEC is just this U naught times N, where again N is the BEC density. And there are some subtleties called the thermal atoms being in different momentum states, but being otherwise identical, feel a factor of bosonic factor of 2, so they will fill the BC with twice the density. But that's not so important for this course. So we have something we can model with the contact potential over given strength. Okay. And this slide is related to our neutral atoms and van der Waals interactions. And there's a letter B appearing in it. Okay, the range of interactions. But the next slide, I kind of started again, right, and from a different angle, coming from a different course in nuclear physics or whatever, or just general quantum mechanics, right? And I introduced this concept of the S-wave scattering length, A, okay, which I've heard it has been introduced a little bit, but still it bears repeating. Right? So here we have some completely random potential, that just generic thing, right? And then have some low energy particle scattering of it, and psi of R is the regular function. Low energy means that there's almost no curvature here outside the potential, right? Okay, there's almost no kinetic energy there. So over here, in the complicated potential, there's going to be all kinds of wiggles. If I solve this, there's a zero, there's potential infinite at the origin, so the wave function has a zero there. Then it has some number of wiggles, which actually the number of zeros is the number of bound states below it, below the zero energy. But that's not so essential at this stage. So something complicated, and then something simple on the outside, okay? And as usual in quantum mechanics, this may be a hard problem to solve, but conceptually it's solved by solving on the inside, solving on the outside, and metrics and boundary conditions, right? And so viewed from afar, right, the particle doesn't know much about what happened here on the 100 A naught scale, okay? All it sees, is that its phase is maybe a bit shifted because of this interaction, or in other words, the intercept of this asymptotic blue function, which is drawn in green dashed, might not be the original 0, which would be if there was no potential, but might be slightly different. Okay, that's the same as saying there's a phase shift on the function. Okay? And this intercept formally is called the scattering length A. Okay, and then the collisional cross section is for distinguishable particle is 4 pi a squared, just an intuition of where the scattering length shows up, right? And for identical bosons, it's 8 pi a squared again because of symmetrization. Okay. But either way, if the two things I want to say, right? The first one is that the U naught I mentioned in the previous slide in terms of A is 4 pi h bar squared over m times A. It has the right units, and again, it can be 8 pi h bar squared over m times A if this is the potential that the thermal atoms feel. You put this factor of 2 either in definition of U or in front, doesn't matter. But these are details. Right? And so from this mathematical form, you see that A bigger than 0 means repulsive, A less than 0 means attractive. Okay, you can take it on faith that this is true. You can also get some intuition from this drawing on the left. So this is basically kind of Heisenbergian picture. If this A is positive, right, that means that the 0 of this wave function is such as if the particle, the scattering particle, right, is localized to some smaller region of space, right? There's an excluded region of space, because it cannot go between this intercept A and the actual origin, right? And so because there's an excluded region of space, the particle is localized to a smaller region, and so its energy goes up, right? This is Heisenberg kind of localization energy. And on the other hand, if A is negative, right, that means this intercept hits here on the left where no space exists, right? So somehow you have stolen, into some virtual space in order to get the flatter function be more delocalized and lower your energy. That's a vague intuition. I'm probably going too fast, but maybe it'll come back to you when you read upon stuff or you run into it again. The other question I want to address, and that's really the main part that Thomas asked me to cover, is why do I have B on the previous slide and A on this side, and isn't A the same thing as B? So B is, as I said, formally the range of interaction, right? And A is the scattering length. But if I tell you things like, sigma equals 4 pi a squared, it's quite intuitive that B should maybe be roughly the same thing as A, right? Because you imagine that, like, if I'm passing through some world and I scatter, I must have passed through that region where we interact, right? So there is some intimate relationship between B and A. And that's a good intuition, and it's true most of the time. But at the same time, it turns out that the subtle difference between B and A is crucial for a lot of the success of this field of quantum gases. So here on the left, and I'll show you more in the next two slides, but here on the left, you can imagine, now that they have defined A in this seemingly formal way, but it turns out to be correct and even somewhat intuitive, you can imagine that if I change the potential just very little, right? If I change the shape or something a little bit, the range of interaction will still be about the same, okay? The drawing doesn't change much, right? But A can change a lot, right? Because if I change this vehicles just a little bit, the phase shift or this intercept can change a lot, right? It can actually, intersect somewhere at minus infinity or at plus infinity or anything. This is at the heart of so-called Feshbach resonances that I'm going to tell you on the next slide. But before we get there, just to reinforce that this idea that the intuition A equals B is not so stupid. Well, I'm already out of time. Okay, fine. This is a real calculation, which you can take on trust. It's really just like calculating inside, calculating outside, matching boundary conditions. And so if you have a repulsive potential, fixed range of interaction, B, okay, and vary the strength of this potential, then in the limit of infinitely high potential, here K naught is just the root of the potential, A goes to B, right? And this is intuitive, right? If this region, R less than B is completely excluded, obviously the intercept is just where you hit the y-axis, right? But there are atoms have attractive potential, and then things can get more complex, as in the drawing on the previous slide. So again, if I fix B and I change this V naught and do the same kind of calculation, then you see something much richer, right? Yeah. So actually, statistically speaking, most of the time, this is this red line, most of the time A is equal to B. Right? However, every so often something crazy happens, right? A actually goes down to minus infinity, appears at plus infinity, and so forth. And these are these places like where a small change in the wiggles of the short range wave function dramatically change the intercept. And it turns out that those coincide actually with the appearance of the new zero. Sorry, let me try to go back. Well, not that way. Okay. With the new zero in the short range wave function, i.e. a new bound state in the system, right? which is now associated, familiar association with our molecules, because our molecules have bound states, right? Their scattering molecular potentials have bound states. And so if only, with a fixed B, if only we could somehow stretch this V naught in some clever way, very gently, very precisely, okay? Then, we could change the scattering length at will and make our gases, attractive or repulsive, strongly attractive, strongly repulsive, weakly attractive, weakly repulsive, whatever we want. And it turns out we can do that, okay? Not in the simple form with the square well, where I can change the depth, right? But it's essentially the same effect that is provided to us by the so-called Feshbach resonances. And so I spent 2 minutes on Feshbach resonance. I'm sorry, I am running over time, right? I'm supposed to finish now. Is that correct?
That's correct, but that's fine. Until
Okay, fine.
15, 20.
So this is the idea of a Feshbach resonance, which is basically like a trick, your knowledge of atomic physics. We have 120 years of atomic physics, and so we know how to play with our atoms, and we can effectively create that thing where we very gently change the depth of the potential. And the reason we can do that is because our atoms have a rich internal structure. Okay? And specifically, they have some different spin states. This is very generic. You don't have to think what spin states are involved here. But suppose that the two atoms can be in two different spin configurations, which have different energy. And so one of these, black and red, are drawings of the scattering molecular potentials for atoms which happen to be in spin configuration A or spin configuration B. Okay. Now our atoms are actually, this is the relevant scenario, our atoms are actually in spin configuration black, okay, and they have very little energy, very little kinetic energy, so ultra cold atoms, so essentially zero energy scattering. And this other configuration, call it red, actually has higher energy, so it sits above. Right? Now we don't, as I said, the magic would be to tune the depth of a square well in order to tune the scattering length. What we do instead is because these guys have this different spin configuration, they have different magnetic moments, and so by simply applying the magnetic moment, we tune the relative position of the red and the black curves. Okay. And so the same resonance effect that I told you about before basically happens when the bound state in the red potential happens to be aligned with the zero energy of the black potential. Okay. Now the reason that happens is because this drawing is a bit wrong. Okay, so they're not actually decoupled, spin channels as we call them. Okay, there's some complicated coupling at short distances, and so when atoms get very close, they can temporarily actually jump into at least temporarily jump into the other spin state, or these things are mixed, or however you want to think about it. And so if it's so, and then they have to leave, right? They cannot leave on the red channel, because that's some positive energy they don't have, zero energy scattering. So they can only leave back in the black spin configuration. But when they're close distances, they dance and they probe all kinds of interactions to see whether they can make the marriage work, right? And if this red molecular energy level is exactly zero energy, then it takes them longer to figure out they cannot make the marriage work, right? They don't have the right energy to stay there, right? And so they spend more time, and there's more effect on the cumulative phase shift. There's effectively stronger interaction, and the larger scattering length. Right? That's the basic idea. And so just by tuning this red with respect to the black, and let's focus on one resonance, but this will happen every time a molecular state passes the zero energy threshold, we get this ideal tuning tool where in the vicinity of such a resonance, this is a magnetic field, scattering length, we get this dispersive shape where we can make the scattering length arbitrarily large or small, positive or negative. Okay, and this is the generic mathematical formula that describes it. There's some background scattering length when you're away from the resonance, and then you have a divergence as you approach the resonance at the position B naught. Now, this is beautiful, okay, but there's another thing that comes with it, and I don't know if you know anything about it or not, but now you'll know a little bit about it, and it'll be relevant for non-equilibrium studies. And this, unfortunately, I could spend the whole hour on, but I can't because I don't have it. And that's that when we enhance the scattering cross-section and we enhance the nice elastic collisions, which is the heart of our beautiful many-body physics, which is what we wanted to do, we also enhance something called three-body loss, recombination loss in the atomic gas. How many people have heard of three-body recombination loss? Everyone, almost. Okay, on my small screen, more than half. Okay, so it's good to mention it. I cannot fully cover it here, but basically, the point is that it's actually kind of gets into a non-equilibrium story. Is that our BEC with everyone in the ground state and so forth is not the true ground state of the system. The true ground state of the system is a lump of metal, right? At these temperatures that we're talking about, like all these alkali atoms that we usually work with, but also other ones, would like to be just a chunk of metal. Right? And the reason they're not a chunk of metal is that they don't actually reach this kind of whatever you call phase equilibrium, because in order to make a solid state system, you have to make some kind of cluster. In order to make a cluster, you have to make a diatomic molecule. Okay, and in order to make a diatomic molecule in vacuum that's actually not so easy. It requires 3 particles to meet. Okay, because if 2 particles meet and they try to get married because of some binding energy, right? There's a problem that now suddenly they have kinetic energy, but they have no momentum. Right? And so you cannot, in that process, consider both energy and momentum. So you need 3 guys to come together, 3 atoms to come together, so the 2 can become a molecule, and the third one splits away, and then they share the kinetic energy, so the total momentum is 0. Okay? So creation of molecules is only possible when diatomic molecules is only possible when 3 atoms are present. And the whole history of this field is based on the idea that we reduce the density so that the 3-body processes, which scale as density squared, you need density squared to meet two other people, right? Are much slower than the 2-body processes, the good guys, which scale as density, right? And this relative scaling remains true even if we enhance A. However, as I've shown you before, good things like mean field energy scale like linearly with A, and the elastic collision scale quadratically with A, whereas this 3-body recombination process scales as 4th power of A. Right? And so we increase the relative importance of this 3-body recombination, which is usually not good. They can also lead to things I can teach you in this course, thanks to the 3-body recombination. The basic, if you want, as the last thought for today, the basic idea is like, is that if the atoms here, going to the drawing on the left, I'm sort of moving my mouse, but I don't know how visible it is that if 2 atoms spend a lot of time in there, dancing with each other and deciding whether they can actually be a molecule, this loose molecule or not, the more time they spend there, the more likely is that the 3rd atom comes and bumps into them and quenches them into some deep bound state here. And then they're gone from our story, and a lot of energy is released. So we can tune interactions, basic messages, we can tune interactions, right? But it comes at some cost of enhanced 3-body recombination, which in lowest, simplest theory goes as A to the 4. Okay, and these 3-body losses will also feature in our non-equilibrium studies. And so with that, I guess this is a good place to stop. It's going to be horrible how slow I am, but okay. So we did the part 1. Okay, I thought it was going to be less than 1 lecture, but it wasn't. Which is some general motivation and what is the difference between universality, seeking for universality, and simply doing stamp collecting. And we have covered all the experimental tools. So we understand we're going to have these homogeneous systems. We understand we're going to be able to tune the interactions. Okay. And then I guess it's going to be 1 lecture each. Basically, like I'm going to split the rest right into 2 subsets of examples of non-equilibrium physics. Okay. And there's multiple reasons why I split it into these 2 stories. One is that part 2 involves losses as key players and part 3 doesn't. Okay. Another one is that part 2 is kind of unintentional non-equilibrium stories. So these are the things that we ran into, not because we wanted to study non-equilibrium physics, right, but because they inevitably happen. Whereas part 3 are generically, paradigmatic non-equilibrium stories that have been studied on purpose. a very related issue is that like, in part 2 is not just that we didn't want to study non-equilibrium, but we wanted to study something equilibrium. And so that's why this part 2 connects better to what I'm guessing you have been learning in other courses, and including things that we have studied today. What is Bose-Einstein codization, saturation of excited states, and basic things like that. Right? And finally, because the physics is similar, the maths will also be similar. So in part 2, we'll be doing more things, more explicit maths, be more connected to things that you already know, and you can, at least between lectures, try to recover yourself. Right? Whereas part 3 is more about, completely new formalisms that are used for non-equilibrium physics. Right? So in all kinds of ways, I felt that that part 2 is closer to you now, but on the other hand, part 3 is closer to this idea of universality. Right? There, it's 3 paradigmatic problems, and you see how they actually fit together. Right? They're all famous in their own right, but they illustrate how we can get to some kind of universality far from equilibrium. And so I think with that, we're going to stop, right?
I think if we have questions,
and
a good
what
thing
I'm going
is...
to do, I think, is send Thomas just these slides for the first one, so you have a reminder to look over them before the next lecture. But
Okay.
there can also be questions, yes.
Yeah, we can take questions, I think, and a good thing is maybe if you come down here to ask the question, it's easier than Zoran instance. Well, but if there is any, but please. Can you come down? Sorry. You're sticking the microphone in addition.
I had one question about the 2 slides back. I think.
Yeah.
This one. Sorry. The next slide.
So which one?
In the next slide, you were
Next
talking
slide,
about
okay.
these two spin channels, right? So I was wrong. In the black spin configuration, that's a collision between the 2 black spin atoms, right? So would the red be between 1 spin red, 1 black spin, or would it be between 2 spin red, or doesn't it matter for the Feshbach resonance?
It doesn't matter for the concept, but also it's not like that. It's not they're combined. So it's more like you have 2 spin half particles which can interact in a singlet or a triplet. It's more in that spirit, right? That like even 2 same guys can mix their spins differently, and they do differently in different distances depending on some
Okay, so
hyperfine interaction.
Could be any
But
configuration.
but you can, they're identical particles, okay? So if you like, you can also think of it as like 2 up is black, 1 up, 1 down is red, and there's no notion which one is up, which one is down, right? Because it's So you could just say like black is the same spin is not the same, right?
Okay.
The red is not the one, right? And actually, like they are mixed at short distance. So really, this 2 channel is a cop out, right? We used 2 channels because we didn't know how to diagonalize the system, right? The reality is that that they are somewhat mixed. You will kind of do some crossing from black to red in some way, right? And so movement of the relative black and red is really even more like what I was advertising in the previous slide. If only we could change the depth of the square well, right?
Right. Okay, thanks.
Because it's 2 things that you move each other and then you mix them. That's effectively changing the depth, right? But I think for teaching this 2 channel model is easier.
Cool,
Okay.
thank you.
Yeah, just to complement the magnetic Feshbach resonances, when the red and the black are like displaced vertically, like the relative position is displaced vertically with the magnetic field. Just you mentioned
Yes, that's right, because they have different magnetic moments, right? So we
Right.
just apply a magnetic field, and that's how we tune relative red to black. Sorry if I didn't say that, that's bad. Anything else at this stage?
Hello. Hi.
Yeah.
So I know that some atoms have narrow Feshbach resonances, while others have broad Feshbach resonances, and I was wondering how does this happen? And the difference is only that you need a more stable magnetic field, or is it something that narrow resonances cannot be exploited at all?
Whoa. Okay, that's a very hard question.
Yeah, maybe.
Fortunately, I made reference to professionals. So one basic thing, but it's not that simple. It's not just that simple. Is that you can imagine narrow and Feshbach resonances can depend, and now Thomas might be laughing in the background, but one way to understand how it could happen is just what is the difference in these magnetic moments,
Okay.
right? So I have significant change of the scattering length when the bound state is very close to zero, right?
Okay.
Yeah.
Yeah.
And so if the difference in magnetic moments is huge, then as a change in magnetic field, like it will just run through it very quickly.
Okay.
Right?
Okay.
Okay. Now, of course, there's all kinds of renormalization of these magnetic moments when you properly solve the problem. They actually end up being quasi-parallel. And so it's not just like if you say like, oh, singlet has 0 and triplet has 1 mu b or 2 mu b or whatever. Right? Yeah. And so that's the slope. Right? That way there'll be only there will only be a discrete number of widths of resonances. Right? Yes. So somehow depends in a more complicated way on the numerology. There is so that's but intuitively like it's different magnetic moments that can give you to weak or strong so to narrow or wide resonances. At my level of being kind of a many body physicist trapped in a body of an atomic physicist, I would say like narrow resonances are just annoying because you need a better magnetic field stability, right? So this also depends on the absolute fields, right? So if we have a Gauss wide at 10 Gauss, that can be easier than if you have a 50 Gauss wide at 1,000 Gauss. Right?
Okay. Sure. Okay.
So that's another factor, right? Yeah. But there are also, sorry, Thomas, do you want to add or? Huh?
Yeah, sorry, I think it's time to stop. We really have to respect the time for the lunch. So
Okay,
I guess we have to postpone the
sacred.
questions
That's sacred, yeah.
following to next time.
But maybe the others should feel free to leave and I can just continue with 3 minutes with this student.
Right.
Okay.
There are much more complicated issues, which is if you take a snapshot when you're close to resonance, how many do the molecules really look